Superconductors, one of the universe's greatest mysteries, along with black holes and women.
Our journey begins with insulators. In theory, a perfect insulator would have an infinite resistance, preventing all the movement of charge. Rubber, plastic, and wax are all examples of common insulators.
The next stop on our journey is the conductor. A conductor is anything that allows for the movement of charge. In other words, a conductor's resistance lies between 0 and infinity. Metal, metal, and metal are common conductors, and they are used in everything from iPhones to toasters.
And now, for the final and most important step on our journey, the superconductor. A superconductor is the ideal conductor, a conductor that has zero resistance, not close to zero, not almost zero, but zero.
Indeed, in order for a material to enter into a state of superconductivity, it must be chilled to an extremely cold temperature known as the critical temperature, at which point the resistivity will drop instantaneously and abruptly to zero. For example, magnesium diboride has a critical temperature of 39 Kelvin, which is 5 Kelvin below the mean temperature of Pluto. Based on a superconductor's critical temperature, it is either classified as being low temperature, below 77 Kelvin, or high temperature, above 77 Kelvin.
But superconductors do not only have a critical temperature, but a critical field as well. Certain superconductors, known as Type 1 superconductors, will lose their superconductivity once the surrounding magnetic field reaches a certain strength. Type 2 superconductors act similarly, but have a lower critical field and an upper critical field. Below the lower critical field, the superconductor acts as expected. Between the two fields, the superconductor acts as an imperfect superconductor, and above the upper critical field, the superconductor loses its superconductivity.
Type 1 superconductors exhibit the Meissner effect, in which the superconductor ejects any surrounding magnetic field, only allowing it to permeate the surface of the superconductor up to a depth of about 100 nanometers. This is known as the London penetration depth. As you can see in this video, this causes it to float. Now, Type 2 superconductors exhibit a similar effect, known as quantum locking, or flux pinning, in which the magnetic field is locked into place within the superconductor. As you can see in the video, this causes it to float, but it has a certain stiffness and maintains its orientation more easily. Superconductors are extremely useful. They are used in MRI machines, particle accelerators like a Large Hadron Collider, and satellites like Gravity Probe B, which was designed to measure the space-time curvature near the Earth. Gravity Probe B made use of yet another effect exhibited by superconductors, known as the London moment, in which a spinning superconductor generates a magnetic field that is precisely aligned with its spin axis. Early, the idea of high-temperature superconductors was mentioned. Previously, these materials were not thought to exist. However, now that they have been shown as possible, the search for room temperature superconductors has increased. A room temperature superconductor, if discovered, would revolutionize the world, as no special cooling equipment is needed to use them. Indeed, if someone created a superconductor that could operate at normal temperatures, that person would become extremely rich.